level 1 research, so they have to pay graduate students full-time salary. So they have to like keep more undergraduates in bigger classrooms to get the tuition and then pay graduates. So that's how that works. But all right, let's go through the practice exams. Projector. You guys confident for the exam tomorrow? Sort of? It's good? Any type of problem you want me to go through? I can give you some options. But we can go through some of them from the practice exams. Since I saw that section 2, Dr. Morris uploaded a video.
With like exam problems, are we expected to see more like identifying them or solving them?
Yes, let's go through one of them from the, I think there's a good example over here. Good example over here, okay? Yeah, both. Identify the type and also find out the VL, current and VL. It's basically just the same method, right? Just find out get a voltage measure to the other terminal and then do the KCL. Nothing else. It's pretty simple. So the good thing about here, I think, is for the exams, usually the homework assignments is really difficult, and you have deadlines one after one. But whenever you get into the exams or tests, they're just so simple. I sort of like this sort of things. You got a lot of practice during the homework assignments. You still learn a lot, but eventually you don't have a huge pressure on during the final exam, right? So you have a limited amount of time, but you have to finish like 7 to 8 problems. You usually got a lot of pressure, and some people can do it really quickly. Some people have to take the time. But eventually, it's just a little bit unfair. You just have to push them, get things done within the same time frame. I got a lot of pressure when I was born in China, and so the homework assignments and the daily studying was easier, but the exams are super hard. So that's not good. But I prefer this. If you look at the exams, they are just like super simple. Probably the problem level or the difficult level from the first 5 pages of all the assignments, easier ones. All right. There's a problem on the practice exam. It's a good thing to bring up. V1, V2. Let's say R, B, R, A, R, C, R, D, V out. So let me ask you a first question. What's the type? What kind of type of this amplifier? No, it's not summing anywhere, right? It's not summing in one of the terminals. It's basically difference. Good to bring this up, right? And what about if I don't have this one? What type of amplifier it is?
So differential is not great.
Yeah, that's right. Yeah. You went to class. The name of this it's called a bad difference amplifier. I'm just kidding. No, it's still a difference amplifier, but not as good as the one we recommended. Okay. And also, what is a good difference amplifier? Even though we didn't derive the VL, but it's easy to derive it, right? How do you derive the VL over here? We have learned all the techniques. Let me just challenge you a little bit. You have learned how to do it, right? Negative feedback, ideal op-amp, what's happening? Equal, right? Yes, equal. So you need a negative feedback and ideal op-amp. Ideal makes it what? Ideal is giving you what? So for an ideal op-amp, it's giving you what? Yeah, but it's infinite open loop gain, right? It's because it's ideal. So it has infinite open loop gain and plus negative feedback. We know that V minus equals V plus. Okay, that's where this comes from. So how to find out VL over here? They are equal. What's the voltage here? Yes, it's a voltage divider. It's not V2 anymore. If you don't have anything over here, it's not closing the loop. There's no current flowing through it. What's the voltage here? Oh, it's V2. V2. There's no voltage drop, so V2, right? There's no current getting into the op-amp. But now you have a resistor connected to the ground, so it's forming a circuit here. The ground is forming a loop. So what's happening is there's a current flowing, so there will be a voltage drop. So eventually you got a voltage here, becomes V2 times RD over RC plus RD, right? So which is the same voltage here. Then you can easily list the equation to find out VL. Easily. So it's going to be V1 minus this voltage. Right? I don't want to spend too much time on it, but if the resistors are given, it's not difficult to find out VL by using this equation. Okay? So you will find out that eventually it has to be, like I said, we want this structure to be symmetrical, so which means RB equals RD and RA equals RC. Okay? But I found out from the solution of the practice exam, Dr. Ayn put in the solution. This is already published, posted in Canvas, right? Make sure to download and practice on that. So he was doing this to check the ratio. You can see they are not equal. They're not equal. But the ratios are equal. Okay? Is that valid? I haven't verified it yet. So since we know the equation here, you just plug in the ratios, see if the ratios are equal, see if you are still getting this final gain. I haven't finished that yet. But the thing is, I've never seen a difference amplifier with the different values over here. It may be valid, but my question is why? I mean, if you can make a quality difference amplifier, just grab the same resistors. Why have to keep the same ratios and different values, right? It has a chance for mismatch. But however, theoretically, if you plug into this equation, it shouldn't be very difficult to verify. It may give you the same results. It's not important though, okay? If you have time, we can come back here to derive it and see if that works. Okay, but eventually, just keep in mind, we want to keep these structures to be symmetrical, which means you want the values to be the same. Okay? We'll come back. We still have time to verify if this works. He didn't do it here. He just directly move on, saying, hey, there are same ratios, so we can directly use difference amplifier's gain equation. But no verification here. Okay? But anyway, so if you see a difference amplifier, ideally it should be equal resistors, and have voltage source on both sides. Okay, if you see not equal resistors but same ratio, it's also a difference amplifier. If you don't have this resistor but two voltages, it's also a difference amplifier. Okay, they are all difference amplifiers. What about inverting and non-inverting? Are you able to draw that schematic really quick? So inverting, keep in mind always, it's negative feedback always, right? So no matter what, it just connect the output to the inverting with the negative feedback. You just always have to do it. For inverting, your input signal is from the inverting terminal, and you could either ground it or provide a voltage, DC offset. Doesn't matter, depending on your rails. But if you have this one, usually this will be grounded within the scope of this class. They are not making this complicated. Because usually it's plus minus voltage. Could be VSS. They call it VEE. And minus VEE. So usually for beginners, usually they just give a 15 volts and negative 15 volts for the two rails. So in that case, you can ground the non-inverting and have a input signal connect to the inverting in terminal. So that's the inverting structure. What about non-inverting? What's the first step? Remember? Negative feedback. You'll never go wrong with it. What's next? Yeah, voltage should be here, right? V in. What's next? No, this is shorted to ground with a resistor. Okay? These are just the typical connections or configurations of the op-amps. Sometimes you'll see the non-inverting terminal being flipped to the top. It's very common. It's very common. So it'll confuse you. But still the same stuff, right? You got a voltage input here. What's happening here though? Feedback first, right? And then, you'll see this as well sometimes. What's the difference? Same circuit. Okay? So something you have to know. I think although 80% of you guys probably will never make any mistakes over here, but if I have a inductor circuit like this, this should be pretty simple for you guys. Okay, what's the overall inductance? It's L1 plus, right? So imagine there's a current going in, split. So these are in series here in parallel. Okay. I could have an inductor here, here. Could have another branch. What about this one?
I was just wondering for op-amps, if we ever see these, like, I guess, I don't know, positive feedback, is that just like them trying to give us a trick question? Is it still
No, I think there's just one very specific application requires positive feedback, but I couldn't remember. I just only saw that once in my life.
okay.
It's one very specific application requires positive feedback. What about this? So start from the end, very end here. L3 plus L6 in parallel with L5. Okay? So this becomes one inductor, and these three are in series. So this becomes one inductor, which is this guy, and in parallel with this guy, right? Okay, and then the whole thing plus L1. Any question on this type of problem? Anyone? These are great boosters. Okay, if you see some problem like this, you hope there are 100 problems like this on the exam. So you can. Yeah, so you can get 100 when you're sleeping, right? Done. Oh, done. Okay.
The final just
All right, let's go through the practice exams. Section 2 did it with the video. Dr. Morris recorded 2.5 hours, posted on Sunday. How much more could you ask for? I was like, oh, should I do that as well? We'll do that today, okay? So we're not comparing the two sections. All right, problem 1. Do you have a copy with you? Probably no, okay. So, this guy, this, Oh, this is a really fundamental problem. Let me ask you this. What does that mean? 0 degrees. What does that mean? It's unreal, right? So it's 100. So this is the phasor form. This equals 100 times what? Cosine theta plus. So no magic here, right? So this 0 angle is basically. So this can be converted to EJ 0 degrees. Let's just use 0 degrees, and that's according to Euler's equation. You can convert it to cosine theta plus sin theta, right? It's, let's just use zeros. So this becomes 0, and this is 1. So it's basically just 100 volts. If you see 0 degrees, it's 100 volts. Okay, and this is operating at 500 hertz. 500 hertz. That's interesting, right? So why a DC voltage has a frequency here? Is that a DC voltage? Does it have to be a DC voltage? 0 degrees? But why 0 degrees mean? It's only real form, no. It's not shifting, so it's a reference, right? So we're using this as no phase shift. It's just a 0, it's a baseline. So everything is considered as a shift compared to this source. Or relative, right? So this this guy is 3 millihenry, which is what? J omega L, which is the impedance. That becomes, since it's 500 hertz, it's J 500 times 3 times 10 to the negative third, which is 1.5 J. Right? Why he shows a different value here? Such a simple calculation. Oh, 2 pi. Sorry.
Is that frequency?
Oh yeah, that's F. Sorry, yeah, F. So this is F. Be careful about that. So what's the omega? 2 pi F, right? That's 2 times 3.14 times 500. So I have to use this value. So this becomes 9.42. Okay? So plug that in. So this is wrong, okay? So the impedance here becomes J omega L, which is J 0.003. This is wrong. This is right. Let's do the calculation. Be patient. 2 times 3.04. Thank you. This times 3. Nope. What's the current flowing through it? So make sure you know how to use a calculator for the polar form. What would you do over here though? What's the best way or easiest way for this calculation? For the calculator wise, probably. This is 90 degrees. So this is basically 100 0 degrees divided by 9.42 and what, 90 degrees, right? So this is 100 divided by 9.42 10.62. Okay? Or what? In a rectangular form, converted from this phaser form. This is what? Something J, right? What is it? Negative 90 degrees. Yeah. So one more thing may confuse you guys. Have you thought about this? Why do we do a plus bj as a rectangular form? This is a j. So this is a, I say imaginary, this is real. For the rectangular form of the phaser, are they really added together? It's really interesting, right? You put them together with a plus sign in the middle, but you never add them together. Can you directly add a real number to an imaginary number? You haven't done that before, have you? But why do you still add them together? It's just combining them, right? It's just a sign in front of it. It's just a combination. They're just being put together, but they don't really love each other. Make sense? It's just a sign. You're not adding them.
Is it kind of like vector notation, where you have like
Yeah, I think it's just notation. Yes. Yeah. It's not. Yeah, they put the two parts in there, but you never really do this operation at all. Yeah. So convert these into the phaser notation. A little trap here. What's the phaser notation of this guy? What's the first step? Yeah, convert to cosine, right? So this is 12 cosine, whatever inside, minus 90 degrees. So you should know that cosine theta minus 90 degrees equals cosine 90 degrees minus theta, right? You know that?
What is that double property?
Yeah. So just use a angle less than 90 degrees as an example. So theta is here. In minus 90 degrees is over here. Okay, so it's going to be this one. So that's cosine theta minus 90 degrees is here divided by here. So 90 degrees minus theta is going to be this angle, right? You shift this angle to 0. It's kind of confusing. It's the same number of angles, and they are both at the right side of the coordinate. So it's always getting a positive value for this guy. So they are equal. They're equal. But for us, for the scope of this class, if you don't like this kind of coordinate polar form, could you just remember that or put on your cheat sheet that sine anything equals cosine that thing minus 90 degrees. That's the only thing you need to know. That's it. So what's next? It becomes 12 cosine 377 plus, minus 55 degrees.
I think you forgot the T. 377 T.
No t.
No T?
That's why it's a trap.
Oh, okay.
They're trying to let you use this one as the angle. Numbers and angles cannot be combined, right? So you have to leave this number over there all the time. It's already probably have the t plugged in. So it's just a point, it's not a function. Right? Okay, so you want to combine them if you see a problem like this. It's a number, it's not a degree. So what's a phaser form? Just 12 negative 55 degrees, or 12 EJ minus 55 degrees. This also works. Okay? So you're wondering, hey, this guy equals 12 cosine. But it's the same, right? Negative 55 and 55 is the same value, and minus J. So this is this equals this equals this. And you're thinking, hey, you got a sine, cosine. Is this, are they equal? Are they equal? How did you convert a cosine to another cosine sine form with an imaginary number in front of it?
It's a transformation.
Yeah, it's a transformation, but what's really happening here? Do you have a question on this? Have you thought about this in the past? From here to here, it makes sense, right? This is what we have been doing. And this is this, no problem. They are equivalent. And this is this, depending on Euler's equation. So now you're coming back. Is this the same as this one? Yeah, they are in different domains. Keep in mind, this is in the phasor domain. It doesn't have time in it. That's the time domain equation. Don't get confused. Even though you have cosine, you're thinking, hey, wait, why did we do that? It's a phasor. This is a time domain function. Different. This one doesn't have a time in it. Make sense? Okay. Well, this should be a very simple problem. I'll do it really quick, just in case. Just in case. One quick question. What is this? Yeah, it's sometimes you see, so for all these ceramic capacitors, usually you see in the schematic, they don't have a polarity, but for electrolyte capacitors, there are different capacitor, they have a polarity over here. So depending on their, so ceramic ones usually cannot be designed for a very big capacitance, but for the electrolyte ones, you can go up to like several farads, like for example 1 farad. It's a huge cap. Usually the ceramic ones are in the range from usually like a 10 picofarad to, I'm just giving an estimate, maybe 1 nanofarad is really common. But usually you see some big ceramic ones are going up to like 10 microfarads, but usually it won't be more than that usually. 10 microfarads will be probably the biggest you can see as a common value for the ceramic capacitors. But for the electrolyte, you can use it for the power system. Can go up to like several farads, huge caps. So farads is a big unit, right? So 1 farad is a huge cap. So the electrolyte ones, they don't like. So you have to put this one to a higher voltage potential, and the negative terminal to a lower voltage potential. If you flip them, you get a chance to get an explosion. So that's dangerous. Usually we don't do that, but within the scope of this class, we don't care about the polarities. Sometimes you'll see a curved plate like this, but you don't worry about the polarities at all. Just treat them as a capacitor. Okay, doesn't matter. So C1, C2, C3, C4. So what's C equivalent?
C3 parallel C4.
It's not in parallel, it's in series, but it's just yeah. So it's C3 and C4 in series is giving you this, right? In parallel, like 2 plates merging, like 2 plates merged, right? So you're getting a bigger area. So basically you're adding them together. And plus C1, oh no, like this. Okay? It's a great booster. It's a gift. See this on exam, it's a gift. Thanksgiving gift. What about equivalent impedance? So like I said, if you see non-linear components in the circuit, you just treat them as a regular resistor. Convert it to impedance and never worry about that anymore. Okay? So this is the 5 millihenry. What's that? Yeah, it's an inductor. This is a resistor. And this guy is 1 microfarads. So for this one, it's running at omega is 10,000 radians per second. So J omega L is J 10K times 5 milli. It's giving you 100J. Nope. 50J. So if you see a positive impedance, it's always an inductive load. If you see a negative impedance, it's usually a capacitive load. The reason for that is the J is at the denominator for the impedance of the cap, J omega C, right? So if you times J on the both sides of this fractional number, you are getting minus J and omega C, right? So it's always negative. Capacitive load is always negative impedance. And this is negative J over 10K times C is 1 times 10 to the negative 6, 100J. What's the equivalent impedance? Like I said, just treat them as a resistor. So these two are in parallel, and you are getting 100 ohms. So Z equivalent equals 100 ohms plus 50J in parallel with negative 100J. Right? That's it. Just treat this one as resistance. Natural response. So there's a problem for natural response for sure. Okay. Two problems. Just have to know natural response. Natural response. This is I. So it's been open for a long time, or closed, or has been closed for a long time. So you can see the arrow's direction. So it's been closed for a long time. What's the current? Initial current. What is I? So I is pointing up, right? So what is I? So whenever you have this circuit, the switch closed for a long time, this is getting shorted. It's not in the circuit anymore because this is a wire. So you are getting an equivalent circuit like this. Okay, so current here is going to be I. So what is I? It's going to be negative 30 and a 6 in parallel. Okay, so 30 and 6 in parallel will give you a resistance, and use a volt divider theory, 120 volts times the resistance over here, and divided by the overall resistance. So you're getting the voltage here, right? Getting voltage. This is the voltage here. So use that voltage divided by 6. You're getting the current flowing that direction, and adding a minus sign in front of it, so you're getting I. It's the current going up. Okay? So number 2. KCL for what? KCL works too. You can use KCL as well, yeah. KCL, current, that'll be 120 minus Vx over 3 plus I. So these two current going in equals one current going out, which is Vx over 30, right? Yeah, also works either way. Time constant. So for this circuit, same circuit, for t larger than 0. So after it's getting opened, what's the time constant? So if this switch is open, there's nothing contributed by this part of the circuit anymore. So eventually you're getting this circuit. What kind of response? Natural response, right? It's naturally discharging the inductor through the resistor. So what's the time constant though? L over R, right? So R is 4 ohms, L is 8 milli. So we're getting 2 millisecond. Make sure that you can find out the equivalent resistance for natural response. Okay, it's going to be on the exam. So that's why I'm saying the exam is way easier, since there's not even a step response. I didn't see a step response. Probably will be on the final. I don't know. So easy. Just natural response. Okay. So what is the numerical expression for IT larger than 0? What is it? You'll see that in the solution, Dr. Ian is trying to use the natural response as a special case for the step response equation, which works since we talk about that in the class, right? So it's just a special case. So what's the full equation for the step response? Remember, IT equals what? IL infinity plus IL 0 minus IL infinity times attenuation factor here, right? So for natural response, what are the values you can plug in to this equation? 0 for the final, right? 0 is for the final. So eventually this becomes IL, just the initial current times attenuation factor. Just naturally discharge, right? Like this. So, what is it? So what is IT? When t larger than 0, what is IT? So I0 is something you calculated here, right? So just plug in that number in here, times e to the minus t over 20 milliseconds, right? You can convert this one, flip it to the top. Doesn't matter, it's the same stuff. So you just need to find out the time constant and initial current. The two things you need to find in order to find out the final IT. Okay. So, like I said, for a typical problem, yeah, you just have to know how to calculate all the resistance and voltage and currents in a complex form for a very simple circuit. I'll talk about this for so many times. So this is one of the examples. Inductor, resistor, inductor, resistor. J is 30, it's already provided to save your time. J10, 240, 0 degrees. node voltage to find out VO. Node voltage to find out VO. So Vx here. $240 0 degrees minus Vx over J10. This is 0, right? Plus 0 minus Vx over J30 equals Vx current going down 50. Okay, start from here. What should you do? I mean, there's so many ways to do it. I usually prefer the polar form, but I want to show you both really quick. What can I do here? Rectangular. Let's do rectangular first. What you can do? It's going to be 240. Oh, let's say we want to multiply on both sides of the equation. For example, we multiply J30, right? So we're getting 3 J30 times J30 on both sides of the equation. So this becomes times 3. It's giving you 720. It's a constant. Minus 3Vx plus or minus Vx equals J3 50 Vx. What's that?
Why is it 0 minus Vx over J30 and not V0?
Oh, yeah, I'm wrong here. So it should be thank you. It's making this rectangular form more complicated. So that's why I don't usually use rectangular form, okay? Polar form is better if your calculator can do it. Why? Because you can directly do this. 240 0 degrees minus Vx over 10 what? 90 plus minus Vx over what? 30. You can calculate it. You can just use a calculator to find out the phasor form, right? We have a calculator. So we are doing 30 plus J30. So it's rectangular to polar form. Just directly put 2 30s here and do a convert. And you're getting 42.43, and the angle is 44.99. It's basically 45, okay? Equals Vx over 50. So division here makes easier. So this becomes 24 minus 90 degrees minus 0.1 Vx and minus 90 degrees minus whatever this is, Vx over 42.43, just calculate it. And the angle is minus, just add a minus sign because this is basically this plus 0J, right? So that's 0 degrees, it's only the real form. So you know that this angle at the denominator becomes a negative value if you convert it, flip it to the top. Right? So 1, 2, 3 has Vx. So we're getting 24 minus 90 degrees equals 0.1 Vx minus 90 plus Vx 42.43 plus. You think this is complicated? Actually, it's not because you have the calculator. Keep in mind. See? For the phasor summations, I'll just use a calculator. Just use a calculator. So let's take an example here. So Vx can be factored out, right? So we're getting Vx out. This becomes 0.1 minus 90 plus 1 over 42.43 minus, let's just use 45, minus 45 because it's very similar to 45, and plus 0.02. Okay? So use the phasor summation calculator. Phasor math. Okay? Even though you got a constant, just treat it as a phasor. For example, let's do it. Let's plug from here to here. Let's summing here to here. So 0.02. That's the first phasor. 0.02. Angle is 0. Okay, for constant, angle is 0. So the second one, 1 over that, right? 1 over that is what? 1 over 42.43. 0.024, 0.024, and the angle is negative 45. Okay, choose B2 and sum, then perform the calculation. So got these two added together, it's giving you this value, right? Giving you the amplitude and the angle. And do it again for this phasor. All right, and then move it to the, and then you can calculate Vx. All right, if you don't want to follow the phasor, the polar form calculation, you could also follow whatever the rectangular form calculation from the solution. So how that works? You just have to times something on both sides of the equation. So I believe in here, you just have to times 30 plus J30 on both sides of the equation, I think. Oh, no, you times this, actually. So here, see? Give me 1 more minute, this is important. 30 plus J30 is what? D1 times 30 minus J30, right? And this becomes 900 plus 900. That's how that works. If you want to use rectangular form, this is what you want to do to cancel it, to cancel J at the denominator. So this is how that works. Okay. Either way, depending on how you are good at using the calculator. All right. Hope you'll do well on the exam tomorrow. Yep.